Have you ever looked up at the night sky and felt a sense of wonder? It's a vast, dark canvas dotted with countless stars. We see their light, which has traveled for years, sometimes millions of years, to reach our eyes. This light, made of particles called photons, tells us stories about the universe. But what if there's another story being told? A secret story, carried by particles so elusive they pass right through us, through the Earth, and even through the Sun itself without leaving a trace. These are the neutrinos, the ghost particles of the cosmos. They're all around us all the time, yet we know so little about them. Trillions of these tiny particles are streaming through your body every single second. They come from the sun, from exploding stars, and from the very beginning of the universe. Yet you don't feel a thing. They are almost massless, have no electric charge, and barely interact with anything. For as long as we have looked at the stars, we have wondered if we are alone. It is perhaps the most fundamental question we can ask. We have sent our own messages out into the void, like a message in a bottle thrown into a cosmic ocean. We use radio waves, powerful beams of light, carrying greetings from humanity. We listen with giant radio telescopes, straining to hear a reply from the darkness. But the universe is a very noisy and crowded place for radio signals. Think about the journey of a radio message sent to a distant star. This is where our ghost particles, the neutrinos, come back into the picture. What if we could encode a message not in light, but in a beam of neutrinos? A neutrino message would be completely different. It would not be blocked by anything. It could travel in a perfectly straight line from the sender to the receiver. The idea of using neutrinos to send messages across the galaxy sounds like something straight out of science fiction. And for now, that is largely what it is. The challenges are enormous, almost beyond our comprehension. To even think about building a neutrino transmitter, we would need technology far beyond anything we currently possess. Then there is the other side of the problem: detection. If sending a neutrino message is hard, receiving one is even harder. Even with these colossal instruments, we only catch a tiny fraction of the neutrinos that pass through them. A deliberate message from an alien civilization might be just a whisper in a storm of natural neutrinos. If an advanced civilization wanted to create a galactic beacon, a signal that could be seen across the entire Milky Way, neutrinos might be their best choice. A neutrino signal would be persistent and unmistakable. It wouldn't look like any natural source. It would be a clear artificial signpost saying, "We are here." So what exactly is this ghost particle we call the neutrino? Everything you see around you is made of atoms. And atoms are made of even smaller particles, protons, neutrons, and electrons. The neutrino is a fundamental particle, just like an electron, but it behaves in a completely different way. It has no electric charge and also has a tiny, tiny amount of mass. This combination of having no charge and almost no mass is what makes the neutrino so incredibly elusive. It is the ultimate cosmic introvert. It can pass through your body, your house, and the entire planet Earth without ever bumping into a single atom. This is not an exaggeration. This ghost-like nature is what makes them so difficult to study. The only way we can see one is on the very rare occasion that it happens to collide with another particle, and yet, despite their shyness, they are everywhere. They are one of the most abundant particles in the entire universe. The vast majority of the neutrinos passing through you right now were actually created in the heart of our very own star, the Sun. Deep in the Sun's core, nuclear fusion reactions are constantly taking place. The Sun is a colossal neutrino factory, churning out billions upon billions of them every single second. These neutrinos then stream out of the Sun in all directions. Much more energetic neutrinos are created in even more dramatic cosmic events. When a massive star reaches the end of its life, it explodes in a cataclysmic event known as a supernova. Active galactic nuclei are the incredibly bright centers of some galaxies, powered by supermassive black holes feeding on surrounding gas and stars. Finally, some neutrinos are relics from the very beginning of time itself. They were created in the first few seconds after the Big Bang. These ancient neutrinos would be the oldest things we could ever hope to observe, carrying information about the universe when it was less than a second old. The story of the neutrino gets even stranger. It turns out they are not just one type of particle. Neutrinos come in 3 different kinds, or flavors as physicists like to call them. There is the electron neutrino, which is produced alongside electrons in certain nuclear reactions, like those inside the Sun. In the late 1960s, scientists built the first experiment to detect neutrinos from the Sun. The results were baffling. They only found about a third of the neutrinos they expected to see. The solution, when it finally came, was even more remarkable than the problem itself. Neutrinos are cosmic shapeshifters. As they travel through space, they can spontaneously change from one flavor to another. This discovery was revolutionary. For a particle to be able to oscillate like this, it must have mass. It confirmed that neutrinos are not massless particles, upending a long-held assumption in physics. This shape-shifting ability is a purely quantum mechanical effect, and it is one of the most fascinating things about neutrinos. It is a direct glimpse into the weird and non-intuitive rules that govern the subatomic world. To truly appreciate the potential of neutrinos as messengers, we must first understand how they journey across the cosmos. Imagine firing a beam of light at a solid wall. The light stops. Now, imagine firing a beam of neutrinos at that same wall. The neutrinos do not stop. They pass straight through the wall, the building it's part of, and the very planet it stands on. This incredible ability stems from their fundamental properties. Neutrinos barely interact with matter because they are not affected by the strong nuclear force or the electromagnetic force. This means that for a neutrino to interact with another particle, it must get unimaginably close to it, a direct hit on a nucleus. The chances of this happening are infinitesimally small. A neutrino born in the core of our Sun begins its journey outward. It travels from the superdense core and erupts from the Sun's surface in just a few seconds. A photon of light, on the other hand, takes tens of thousands of years to make the same journey. The photon is constantly being absorbed and re-emitted by atoms. This quality makes neutrinos unique cosmic probes. When we look at a distant star with a telescope, we are only seeing the light from its surface layers. But neutrinos stream out from the very heart of that star, from the nuclear furnace itself. They arrive at our detectors on Earth, carrying a pure, unblemished message from their birthplace. Now let's compare the journey of a neutrino to that of radio waves, which have long been our primary tool for interstellar communication and searching for extraterrestrial intelligence. However, the universe is not an empty, quiet space. It's actually a chaotic and noisy environment, and a radio signal must navigate a cosmic obstacle course to reach its destination. The vast spaces between stars are filled with thin clouds of gas, dust, and charged particles known as plasma. Now imagine that your message has to navigate the galactic center. A radio signal sent through this chaotic environment would be completely scrambled, absorbed, or deflected. The galactic core acts like a giant, impenetrable wall for radio communication. A neutrino beam, by contrast, would face none of these problems. It would be completely indifferent to the interstellar gas and dust, passing through it as if it were a vacuum. Most importantly, a neutrino message would not be blocked by planets, moons, or even the star at the center of the target solar system. This provides a continuous, uninterrupted communication channel. For over a century, we have been sending messages into space. We did not always mean to. Our earliest radio broadcasts, television shows, and radar signals began leaking out into the cosmos. This has created an ever-expanding bubble of human communication around our planet. This bubble is now about 200 light-years across. Our 200 light-year bubble sounds large, but the Milky Way is over 100,000 light-years across. Our signals have reached only a tiny fraction of the stars in our own galaxy. Furthermore, these signals get weaker and weaker as they travel. By the time our earliest broadcasts reach a star just 100 light-years away, they are incredibly faint. Our current methods of communication are like shouting into a strong wind. We can be heard by those standing close by, but our voice is quickly lost in the vastness of the cosmic landscape. We are looking for a message in a bottle in an ocean of unimaginable size, and the ink on the message is fading with every wave it crosses. The limitations of radio waves might actually help to explain a profound and unsettling puzzle known as the Fermi paradox. The universe is ancient and vast, filled with billions of galaxies. So, as the physicist Enrico Fermi famously asked, "Where is everybody? Why do we see no evidence of them?" This eerie quiet from the cosmos is often called the Great Silence, Perhaps the silence is not because we are alone, but because we are listening on the wrong channel. The galactic core acts like a giant, impenetrable wall for radio communication. It is possible that the galaxy is teeming with civilizations that are all chattering away, but they are all stuck in their own little communication bubbles. If a civilization wanted to overcome this galactic wall, they would need a completely different kind of technology. They would need something that travels as if the chaos of the galaxy simply wasn't there. They would need a messenger that ignores walls, a signal that cannot be stopped. Could they be the key to interstellar communication? So this brings us to the core of the idea. Let's imagine a very advanced civilization, one that has been around for millions of years and has mastered technologies far beyond our own. They would have encountered the same problems with radio waves that we have just considered. If they wanted to create a true galactic beacon, they would have to abandon radio waves. They would need to engineer a message that is fundamentally different. This is where the idea of using neutrinos for communication is born. We have already seen how neutrinos are the universe's ghost particles. A neutrino beam could be aimed directly through the heart of the galaxy and emerge on the other side perfectly intact. It is the ultimate solution to the problem of the galactic wall. So what would such a message look like? It would not be a natural phenomenon. An artificial neutrino signal would be different. It could be a tightly focused beam, like a laser. It could be pulsed, flashing on and off in a clear mathematical pattern. A sequence of prime numbers, for example. Any of these characteristics would be a clear and unmistakable sign of artificial origin. Let's summarize the argument for neutrinos as the ultimate communication tool. First, they are unstoppable. A neutrino message is guaranteed to be delivered. It does not matter if the target planet is behind its sun or if the entire galactic core is in the way. The message will pass through all obstacles as if they were transparent. Second, a neutrino message is private and direct. A tightly focused neutrino beam would be more like a private, secure line. It would travel in a straight line from sender to receiver, and only the intended recipient, with their detector pointed in precisely the right direction, would be able to receive it. Third, the signal is unmistakable. As we have discussed, an artificial neutrino beam would have characteristics that make it stand out clearly from the natural background. Finding such a signal would be the astronomical equivalent of finding a perfectly cut diamond on a rocky beach. It simply could not be the result of natural processes. The idea of sending a message with neutrinos is truly captivating, but we must move from imagination to the stark reality of physics. How would one actually build a neutrino transmitter? The answer is that it would be one of the most difficult engineering projects ever conceived. On Earth, our most powerful tools for this are particle accelerators. To generate neutrinos, you need to trigger specific nuclear reactions. We smash high-energy protons into a fixed target. This violent collision creates a shower of new, unstable particles. The amount of energy required to power the accelerator is immense, comparable to the electricity consumption of a small city. And this is just to send a weak beam a few hundred kilometers. To send a detectable signal to the nearest star would require energy on a scale that is simply beyond our civilization's reach. It would need an energy source that dwarfs the entire output of humanity today. This is the first great hurdle of neutrino communication creation. It is a task for a civilization that has mastered energy on a planetary or even stellar scale. Let us assume for a moment that an advanced civilization has overcome the challenge of creation. Now, the second great challenge begins: detection. If creating a neutrino beam is hard, catching it is arguably even harder. A neutrino message would not ring a bell or light up a screen. To have any hope of detecting a neutrino, you need a very large and very patient detector. Take the Super Kamiokande experiment in Japan. It consists of a gigantic cylindrical tank filled with 50,000 tons of ultra-pure water. On a very rare occasion, one of the trillions of neutrinos passing through will strike an atom. This creates a cone of faint blue light, known as Cherenkov radiation. However, even with this colossal detector, we only see a tiny fraction of the neutrinos that pass through. An artificial beam from a distant star would have to be incredibly intense for us to notice it. It would be like trying to find a single, specific needle in a cosmic haystack the size of a galaxy. We would have to be looking in the right direction at the right time. Despite these immense challenges, humanity has already taken the very first tentative steps in neutrino communication. One of the most famous examples took place at Fermilab near Chicago. Scientists used their NUMI beam to send a simple message. The message itself was the word neutrino, encoded in the binary language of ones and zeros. The beam was aimed through 240 meters of solid stone towards a detector called Minerva. The Minerva detector successfully received the pattern of pulses. After a few hours of decoding the data, they reconstructed the original message. The experiment worked. It was the world's first demonstration of sending a message using a beam of neutrinos. The data transfer rate was incredibly slow, just 0.1 bits per second, but it was a monumental proof of concept. These early experiments are like the first tentative sparks struck by our ancient ancestors. They are not yet a roaring fire, but they show that the potential is there. Let's allow ourselves to speculate for a moment. Let's imagine a civilization that's 1,000,000 years more advanced than our own. What would their communication network look like? Having mastered energy on a stellar scale, they might have built what we could call a Galactic Internet. The backbone of this network would almost certainly be made of focused neutrino beams. This Galactic Internet would be a marvel of engineering. Imagine a network of automated relay stations positioned in the empty space between stars. A message from a colony in one spiral arm could be beamed to the nearest relay station, creating a point-to-point connection that could crisscross the entire Milky Way. The messages could be anything, from scientific data and cultural works to simple greetings between worlds. It would be a network that binds a galaxy-spanning civilization together. So, what does this mean for us? It means we might be living within a vast web of communication that's completely invisible to us. If such a network exists, how could we possibly find it? We cannot simply build detectors to cover the entire sky. We need to think strategically. We need to consider what an artificial neutrino signal would look like and how it would differ from the natural background noise. Nature, for all its power, is chaotic. An artificial signal would be a model of order and intention. The first thing we could look for is a monochromatic beam. This means a stream of neutrinos where every single particle has the exact same energy level. Another clear sign would be timing. Imagine seeing a sequence of flashes that follows a pattern of prime numbers. 2 flashes, then 3, then 5, then 7, and so on. Finally, we could look for a signal with a very narrow, focused direction. A signal from a distant star system would appear to come from a single, fixed point in space. Looking for these 3 signatures gives us a concrete search strategy. We are no longer just listening, we're listening for a specific sound. Why would a civilization send a message to us in the first place? A more exciting possibility is that we might find a deliberate beacon. An advanced civilization might decide to build a lighthouse. They might aim a powerful, pulsed, monochromatic beam at star systems like our own, stars that are stable and have rocky planets in their habitable zones. The message itself would likely be simple, a hello in the universal language of physics and mathematics. It would be designed to be easily decoded, a cosmic Rosetta Stone. The discovery of such a beacon would change everything for humanity. It would be the single most important discovery in our history, answering the ancient question of whether we are alone. Even if we never find a signal, the search itself is valuable. By building the detectors needed to search for these signals, we learn more about the universe in profound ways. The search for a whisper from the stars forces us to listen more carefully to the symphony of the cosmos. Whether we find a deliberate message or not, the quest will undoubtedly reveal some of the universe's most deeply held secrets. We have traveled on a remarkable journey, from the heart of our sun to the edge of the cosmos. We have explored the strange and ghostly world of the neutrino. These tiny, elusive particles represent a profound possibility. A neutrino message would be the ultimate cosmic message. It would be a whisper that could pass through worlds. Our current search for extraterrestrial intelligence is dominated by radio waves. But radio communication is fragile. It is the communication method of a young species. An older, wiser, and more powerful civilization would likely have moved beyond such a fragile medium. This is the great promise of neutrino communication. It is the perfect solution for a civilization that thinks on galactic timescales. A neutrino beam would not be stopped by a planet, a star, or even the chaotic, dense core of the Milky Way itself. It offers a guaranteed delivery system. A pulsed, monochromatic beam of neutrinos would be a clear and deliberate sign of intelligence. The implications of this are truly profound. The search for neutrino signals redefines what we are looking for and how we should look for it. For humanity, sending our own neutrino message is a dream for the distant future. It would be a project for a united, global civilization. If we were to detect a signal, it would mark the end of our cosmic isolation. It would be a turning point for our species, a moment that would change our perspective forever. It would be the start of a new chapter in human history, one defined by our relationship with the cosmos and its other inhabitants. For now, the neutrinos continue to stream through us, silent and unseen. They come from the sun, from distant exploding stars, and from the very dawn of time. They carry stories of the universe's past. The great question is whether they also carry stories from its present. Are there other minds out there, using these ghost particles to write messages across the void? We do not know. But the possibility is there. And so we will continue to build our strange and wonderful machines, and we will continue to listen. We will listen for a whisper from the stars, a secret code that could unlock the greatest mystery of all.